Thanks so much for the invitation to be here. I've really enjoyed my conversations and visits so far. I want to start with a little bit of news from the Large Hadron Collider well, earlier this year, the CMS collaboration and then the Atlas collaboration made an announcement that they had observed something new and interesting. They had observed the smallest structure ever created by humans. And it looks like this. I have a pointer. So this is a brief interaction between a top quark and an anti-top quark produced at very low momentum so that they briefly form a bound state. And the scale of the spatial scale of this interaction is about 8 billionths of a nanometer. So 8 atometers. This is not the time of day. And this very brief interaction is a representation of the smallest structure that we've ever created. But what I find interesting about it is that it's also possibly the smallest structure, period. The smallest thing that can exist. Now, that seems like a pretty bold statement, especially given the huge difference between the arguably quite tiny scale of this resonance and the Planck scale, the scale at which distance scales don't really make sense to talk about anymore. That's 17 orders of magnitude, so it seems like that's a pretty wide gap for there to be nothing else to exist. But that's the prediction of the standard model, because if you want to make something very tiny, what you have to do is take the heaviest particle in the model, that's the top quark, and bind it to another one with the strongest possible force, which is the strong interaction. So according to the standard model, this is the smallest thing that there can be. And the standard model is an extremely robust theory when you compare it to the data that we've taken at colliders, basically, throughout the history of particle physics. So it sounds convincing, but I'm sure many of you who I've talked to today, are hoping that the standard model is not the last theory that we'll ever have of particle physics, because there are some things that it does a bad job of explaining. And so you all are looking for alternatives to the standard model, which would predict that there are actually stronger forces or heavier particles that you could consider forming structures with. And I certainly also hope that this is true, and I would like to look for these things. But to look for them, we need a good microscope. And we've built one, an excellent one, as Matt said, the Large Hadron Collider. So it is a proton collider with an energy of a proton momentum of about 7 TeV per proton. That makes it an excellent microscope, as you'll know if you sort of calculate the wavelengths that it can probe using your quantum mechanics. You can use your classical electrodynamics to know why it's large. Basically, if you are going to have protons with that much momentum, then the size of the ring you need to keep them in a circular orbit varies inversely with the strength of the magnets you have and directly with the momentum. So that's the reason it's so big. And so presumably we ought to be able to use this instrument to probe scales even smaller than the attoscale, smaller than the scale of the resonance that I showed you. But protons are composite. And because they're composite, you don't get to use all of the energy that the collider has put into the protons in each collision. So besides being a very high energy collider, the LHC also has to be very bright. It has to create a lot of protons so that even though on average they might get 10% of the collider energy in a collision, you will actually have a chance of seeing the long tail of that energy distribution and probing higher and higher scales just by using a lot of protons. Now, if you have a very bright collider, so 10 to the 11th protons a bunch, and these bunches are crossing every 25 nanoseconds, it must mean that you have to deal with some side effects. And this is a picture of the side effect. This is a picture of, it's not a typical collision, it's a little bit atypical. It has on the order of 150 proton-proton collisions happening in one bunch crossing, 125 nanosecond period. And that's the time window that we use to take data in our experiments. So we see all of these things happening at once, And if something interesting is happening in those events, like the production of this muon going out there, we have to pick that particular event out from all of that noise. So there is a cost to this high luminosity. Nevertheless, this is the collider that we have, and we've used it to explore energy scales. And depending on what processes you're looking for, we have explored them in the hundreds of GeV to few TeV region, which is really sitting right around the attoscale. Obviously, we want to go further to look for smaller structures. And for that, the international particle physics community is now discussing the best ways to do that. There are a couple of options. One is to scale up the LHC, and magnet technology has improved, but not so much. So if you want to increase your energy by an order of magnitude, you've got to increase the size of your collider by a similar order. So this would be a huge full circular collider built near the site of the original LHC. And this could have around 100 TeV, somewhere between 80 and 100 TeV of energy, which would translate to about an order of magnitude increase in the energy per parton in proton collisions. Another alternative is a muon collider, which can be much smaller because muons, unlike protons, are point-like particles. And so every time you collide them, you get all of the energy every single time. And a muon collider could be smaller and still give you access to the same range, an order of magnitude higher than what we're already probing with the LHC. So this sounds great. It's a big step forward in the energies and therefore the distance scales that we can probe. But the dates are highlighted in this diagram here. And for me, 2050 or certainly 2070 is too long to wait. So if we want to see things a little sooner, we have to use a trick. And it's a trick I think you are all familiar with. There's a quantum advantage for colliders, which you can think about in terms of the double slit experiment. So if someone gives you an electron beam and they simultaneously give you some unknown collection of apertures, then you can figure out by examining the interference pattern made on the screen exactly what configuration of apertures you were given, right? And you can do this basically single electron at a time or the entire beam at once because it's a quantum effect. This also happens in hadron colliders. In general, for a proton initial state, there are many ways to make a particle such as a Higgs boson. And if there are multiple paths, then just like the electrons, those paths should interfere and cause changes in the probability distribution that we measure when we look for events with Higgs bosons in them. And it doesn't really matter whether or not you have enough energy to create the particles in the intermediate state here, just like it doesn't really matter if it seems likely or not that the electron would go through the lower slit. It will have an effect on the distribution. The only thing is that as the energy becomes less and less accessible, its impact on a figure like this will be more and more subtle. So this is an argument that if we want to look for high mass, small distance scale phenomena without having high energy, we will at least need high precision. So the international physics community also knows this and is thinking about it. And so in between the time that we work on constructing and designing these new colliders and where we are today, there's the idea to make a look at lower energy machines. But you'll notice that all of these colliders are lepton colliders. And they could be built on a slightly shorter time scale than, say, the muon collider or a full circular collider. Now, these alternatives differ from the hadron colliders in a way that I hope is illustrated by these pictures. These are pictures of a supersymmetric process that you don't have to pay attention to. The point is that the same process looks very different at a lepton collider and at a hadron collider, right? These, in the lepton collider, you know that the energy you see is the energy you put in. In the hadron collider, you don't know that. You don't even know the momentum, the total momentum of the intermediate state that you produce. And there's all this noise. This includes some pileup, but a lot of this noise is generated just from one proton-proton collision because protons have a lot of partons in them, and they're messy. So for precision, rightly, the physics community is looking at lepton colliders in the initial state. And that also makes sense when you're looking at what should be in the final state of the events that you study for precision. So if you think about what precision means, the shade of blue doesn't show up very well, but for any measurement, there's a statistical component and a systematic component. The systematic component is obviously dominated by what you don't know about the state that you're studying. So in the standard model, you know a lot about the things that you could measure directly. And that happens to just be these three particles. Those are the only three particles that our colliders can see directly. Electrons, muons, and photons. There are many more that can be reconstructed from decays without too much difficulty. And for these, the systematic uncertainties are larger because you're adding together uncorrelated things to get the properties of these particles, but they're not insurmountable. But everything else in this picture is not observed directly. It's not reconstructed from decays. It's just inferred from jets. And so for a precision measurement for small systematic errors, these jets are going to make things difficult because instead of a few particles to reconstruct in a decay, there can be hundreds. However, there is a slight statistical advantage to looking at hadronic final states instead of leptonic. Because, and this is the standard model chart that I would have on my wall if they printed one so large, it reminds us that there are three kinds of quark for every lepton. So in the decay of interesting heavy particles, assuming to 0th order, basically, that they couple universally to fermions, it's mostly going to be quarks. We're going to have to deal with them. And so the bulk of my argument or discussion with you today is that it makes sense not to completely ignore the jets, to see what kind of precision physics we can do with quarks. And to do that, I will explain to you for a little bit what a jet is, what we have learned about them and what kind of physics it's brought us, and a little bit about what that means for the upcoming era in particle physics. Okay, so we'll start with what's a jet. It's late in the afternoon and I only had half a coffee. You guys might also be tired, so I'm gonna ask you. In this figure, an event display from a simulated, idealized collider detector, how many jets do you see? I want to see a show of fingers. See, 2, 3, 3, 3, 5, 3, 3. Okay, I see. So this is really good. I'm not going to have to teach you guys about jet clustering algorithms because you can already do it with your eyes. Yeah, so there are 3 jets in this event. And how many partons, how many particles do you think were produced in the hard scattering interaction, the initial interaction before anything else happened when in this simulated event? You see a 3, fingers up, guys. I see some 2, 3, 2. Yeah, so 2 or 3, I'll accept either answer because it really depends on your cutoff scale. Yeah, so this could have been a 2-jet event with radiation or a 3-parton direct process, depending on the quality of the simulation that you're using. But that's right. So you guys know what jets are. They are the manifestation of a parton, a quark or gluon, after it has endured the parton shower. It's what we see in our detectors. And the way that you can get many, many particles, the 100 or the dozens that you see here, from 2 or 3 particles, are the processes that you're familiar with, the 2 to 3 processes that can happen to elementary particles. So Bremsstrahlung, pair production, or decay, right? All of these processes happen in the production of a jet. The most important, however, are the Bremsstrahlung and the pair production. So the QCD looks a lot like the QED that you're familiar with major differences being, of course, the non-abelian couplings. So gluons can either radiate or pair produce gluons. So I think you can choose what you want to call it. But the shape of this process, what it looks like in the detector, which you guys so quickly identified, is really because of the structure of radiation in a field theory like this. So the probability of radiating a particle with a momentum fraction z, so the fraction of the initial parent particle's momentum, and an angle theta basically goes as dz over z times d theta over theta. And that means that they're infrared and collinear singularities. This is also nearly a scale invariant process. Interference makes it angular ordered, which is a lot to take in, but it really means that jets are these fractal objects that have a cone shape. And the final thing we have to remember is that jets are colored particles, and colors seem to be confined. So at the end of all of this, somehow, automagically, they turn into color neutral hadrons. Right? Okay, so this is what a jet is like. How do we measure it? Well, in ATLAS, we use our electromagnetic, shown in gold, and hadronic calorimeters. So there's lead liquid argon, we keep going too far, lead liquid argon calorimeters here that allow us to detect most easily electromagnetic showers. And then the very large calorimeters are there to catch the hadronic part of the shower. The only way we can measure a jet is to destroy the particles in it. Because unlike, say, electrons or muons, in order to capture the entire jet, we just need to measure all of its energy. So the particles are absorbed basically in the calorimeter. And our calorimeters, not because we wanted to study jets, but because we got lucky, have segmented and very granular readout, which means that there is a small ability to know the direction of the particles as they pass through the calorimeter. And when we measure the energy, we basically take the shower shapes that happen inside of the calorimeter or the pulses of light from the hadronic calorimeter and translate those into energy measurements. So what we get is an okay direction and a pretty good energy measurement for the particles in the jet. And to go back to understanding what the original particles that created them are, we have to do some sort of reconstruction procedure. So from the measurement, we can infer the energies of all of these hadrons. And then we just sort of make the assumption that these hadrons are a good representation of the partons that were created in the event. And we use the clustering algorithm, which, like I said, you guys did by eye, in order to associate those objects with the directions and properties of the original parton. So there are a lot of steps, a lot of subdetectors involved, and it sounds pretty complicated. So you might want to ask yourself, how does it work? And the answer is sort of. Yeah, it sort of works. There are many problems that complicate jet reconstruction. For the individual hadrons, the detector's response to them depends on a lot of things, like where it went and what kind of hadron it was. When you measure the energies in the calorimeter, some of it was not coming from the jet you're interested in, and some of it was not even coming from the collision that you're interested in. It was coming from the pileup of those extra interactions. And then after you have the hadrons, you could ask yourself whether the clustering algorithm works really well. My presentation keeps wanting to get ahead of me. And the answer is, yeah, it works okay. So our first lesson is going to be how to improve jet reconstruction so that we are able to do precision physics. So our target that we define is not going to be to recreate the energy momentum for vector of the original quark or gluon, because that's a very model dependent idea, and different calculations will map onto that object in very different ways. So instead, what we're going to try to do is just get the momentum sum of all of the hadrons right and leave the rest to things that we can correct after the fact. So we'll start with reconstructed jets, the reconstructed hadrons that we see. We'll have to correct for the pileup. And then we will have to correct for our simulation. Now, our simulation is excellent, and I want you to compare these two pictures, one of which is taken from the vertex positions of electron-positron pairs created in photon conversions, and the other, which was simulated, but the same process. They both show a very zoomed in view of the innermost part of our tracking detector, and the simulation looks pretty good. It's hard to tell these two pictures apart. But if you look in the corners, you can see a difference between the filled in holes here and the open holes there. And that's because our simulation at this time didn't have the correct description of the fluid that was flowing in the cooling pipes of our silicon detector. And these kinds of differences can lead to a different expected response of our detector. So in order to get this very right and do precision physics, we need to use actual data to calibrate the measurement of jets. And there are a couple of ways to do that. The first is momentum balance. So I don't know much about the quark-quark or gluon-gluon collision that created the jets in the LHC because, as I said, protons are composite, so it's messy. But I do know that they had no momentum at all in the direction perpendicular to the beam. So for momentum conservation, I can calibrate my jets by asking that the momentum that a well-reconstructed particle like a photon has matches well with the energy of the jet. And I can derive this correction by looking at a lot of photon jet events where the jet hits in all sorts of different places in the detector. So the momentum balance method is a very straightforward way to learn the energy scale of your jets, such that the jet energy scale becomes the photon energy scale, which is much better known. But there's another method. If you had single hadrons and you could shoot them through the detector and measure their responses, then you could just convolve all of their responses and add up a jet, and you would get another measurement of the jet energy and its uncertainty. This constituent-based method makes sense. And when we first turned on the Atlas detector, we tried it using test beam data, but it came with very large uncertainties. Just this year, Atlas has finally used not just test beam data, but other sources of data, such as W bosons, which produce tau leptons, which produce hadrons, in order to create a detailed calibration of individual constituents, jet constituents. And that calibration is shown in the cyan blue here. Whereas the balance methods, you can see, run out of statistics either at the high end or the low end for the gamma plus jet and Z plus jet. So we learned two things when we made this plot. The first is that what we were doing with momentum balance and what we were doing with the hadrons match up quite well. They both say that the detector is seeing about 97% of the jet energy over here, and it goes up a little bit on the other end. But the other thing is that since they agree very well, then we can reduce the uncertainties in this region. And this is the region from about 100 GeV to a TeV, which is a region that's really interesting for looking at the decays of heavy particles. And we can apply that to make a precision measurement of the top mass using jets. So to do this, we find events where there are two top quarks produced. One decays to a lepton, and we basically ignore it. The other one decays to jets. And we basically add up the energy and momentum of these jets. We use what's called a boosted topology, which does two things. The first is it puts these jets in the region where we have a very good calibration for their energy. The other is that the Lorentz boost collimates the top decay so that the two quarks from the W boson and the B quark are all sort of in the same region. That way they catch less pileup, and they're also, they catch less pileup, and it's hard to confuse them with the jets that came from the other quarks display, the other top quarks decay. And then we do a simultaneous fit to the mass of the top quark and the mass of these two jets together, which make the W boson, which is very well known, in order to constrain systematic uncertainties. This is just to show how nicely the fit to the W boson mass comes out. And these are the primary uncertainties. And here's the result of our measurement. And the uncertainty on this measurement of the top mass is about 500 MeV. And it's the best measurement that Atlas ever made, even though we have used leptons for precise top quark measurements before that. I will admit that CMS has a more precise measurement right now using a different technique, but complementary techniques are really nice for a very precise LHC average. So can this top mass probe the Planck scale? Many of you may know that Higgs coupling parameters like the Higgs mass are sensitive to the mass of the top quark. And so if you vary the mass of the top quark by about 3 or 4 GeV, it will change the running of the Higgs quartic coupling such that the place where it becomes zero can vary by something like 6 orders of magnitude. It's very sensitive. And in case you don't recall, the Higgs quartic coupling is what makes the bottom of the wine bottle and the Higgs potential turn up. So when it becomes negative, no more stable vacuum. So even more precise measurement of the top mass. This is already an error band that's about 8 times bigger than the uncertainty of the measurement I just showed you. But if we can make it even smaller, then we can constrain that region of physics even better. And I think for the high luminosity LHC, we have enough information to reach basically half of the total uncertainty that I showed you for that last measurement. So this is really good. Part of that is because the high luminosity LHC will have a lot of luminosity, so the statistics get better, but that only wins you about 10%. The rest is coming from things that we have learned or are soon to learn about jets. Okay, that was lesson 1. Questions before I jump on to the next one?
Jet fragmentation and all exactly. Do you primarily rely on the one string model?
So we use both. So we have cluster hadronization and string hadronization models. And if you look at most of our experimental results that really talk about fragmentation, you will see that we compare those simulations. And I have one plot later in my talk where you'll see that fragmentation is modeled very differently by our different generators for exactly that reason. Okay, lesson 2. Oh, I think it's on autopilot. Right, so lesson 2, we're going to study the Higgs coupling in more detail. We're going to study it directly by looking for di-Higgs production. And we're going to look in a channel where one of the Higgs decays to 2 photons and the other to 2 B jets. And to do that, we have to find the B jets because cases where those jets aren't B jets constitute the major background. So it's possible to consistently label a jet by its flavor because parton showers conserve flavor almost always. We had a discussion about this earlier. So through QCD interactions, there's nothing that can change the flavor of a jet that started with a bottom quark. So you start with a bottom quark and you're going to get a bottom hadron coming out. And since bottom hadrons are long-lived, they will move, half a centimeter or so in our detector. Then you can find these kinds of jets by looking at secondary vertices within the jet. And these secondary vertices can be reconstructed by taking your tracks and extrapolating them from where you measured them back towards the beam spot. And if they don't converge at the beam spot, you have a secondary vertex. So in the beginning of LHC experiments, that's exactly what we were doing. And then machine learning became a thing. And we started throwing our various ways of estimating vertex positions into neural networks and boosted decision trees to make a better discriminator between light flavor and bottom flavored jets. So that's where we started. And this is probably about a 2015 plot. And then we started keeping up with the flow and the evolution of machine learning algorithms until we started using transformer-based algorithms a few years ago. And you can see that our ability to reject charm jets and light jets while keeping the same efficiency for keeping bottom quarks has increased since then by a factor of about 6. So this is excellent because a factor of 6 smaller background makes any analysis easier. And so we've applied these transformers to the di-Higgs search. So this story is really the kind of boring story of we used AI and everything got a little bit easier. So if we look at events where the Higgs is decaying to 2 photons, this is actually a tiny fraction of possible di-Higgs events. 2 photons are very rare, 2 B jets are more common. And putting them together, you get a kind of decent acceptance for the analysis, while still being able to use the very clean measurement of a Higgs decaying to 2 photons to separate your signal from background. Applying that as well as some machine learning also to sculpt the shape of the B-jet mass distribution, the di-B-jet mass distribution. Atlas's latest result with run 2 and 3 data looks like this. So the background here, this little dark bump, is normal single Higgs production where the B-jets are just from background. And the red is the sum of signal and background. We have not made a significant observation of di-Higgs production yet, but this is one of probably 3 or 4 very promising channels done with low luminosity LHC data. So first of all, even if you don't observe di-Higgs productions, you can set limits on it, and that leads to limits on new operators, which would enhance this cross-section. These can be interpreted in various frameworks, either Higgs effective field theory or standard model effective field theory, slightly different parameterizations, but the answer is we don't see anything unusual, so it doesn't really matter. But the most important takeaway from this is that, again, by learning to better tag jets, something that wasn't possible at the HLLHC becomes possible. So we are able to project that now, not only can Atlas and CMS claim observation of, or future Atlas and future CMS can claim observation of di-Higgs production, but we ought to be able to measure to somewhere between 15 and 30% the shape of the Higgs potential through this observation. So we went from not really being able to claim discovery to being able to claim discovery and then some, just through the improvements that were made in this analysis. Okay, lesson 3 is about dark matter. And this plot we don't have to scrutinize in detail. It basically says that we can look for dark matter being produced at the colliders or look at the messenger particles that could connect the dark sector and our sector, and we have done so and we haven't seen anything yet. Yeah, so dark matter is still missing. The traditional first searches for dark matter at the LHC were looking for missing transverse energy, using that momentum balance that I told you about before, in order to look for particles that were invisible to the detector, because they're invisible to basically everything. And here's one sort of process through which that might happen. Where this extra jet is not coming from any interaction with the dark matter, it's coming from initial state radiation from the incoming quarks in the collision. So we haven't found it anymore. And, I think I have a friend who says that if you want to hide anything at the Large Hadron Collider, you just make it a jet, even if it's something like a cute puppy. The dark matter can also be hidden at colliders by making it produce something that resembles a jet. If you also make this mediator particle carry a conserved charge, then the S-channel limits that I showed you on the previous slide are also avoided. But if dark matter is showing up in our detectors as something that looks like jets, there's a huge theory parameter space of how this could be happening. It could be happening in ways where some of the particles produced through dark ordinary matter interactions are seen and some are not. So there is missing energy, but it's embedded in jets. Or it could happen that the dark matter particles have a lifetime and they just decay somewhere within the detector. So you start with no jet at all, and all of a sudden the jet emerges and starts showing up in your tracking detector. And there are other models in which the shape of the jets formed by dark matter are completely different. So it's a broad space, and to explore it, we have sort of 2 ways to go. We can use model-driven approaches where we know what we think the dark matter looks like, and we are just using machine learning taggers to discriminate between them. Or we can use anomaly detection, where we just train to look for things that don't look like the bulk of the distribution. And we have applied both of these methods in searches. The model-driven searches have matured in very much the same way the flavor tagging searches that I told you about before are, looking for B hadrons and looking for weird jets with long-lived dark matter in them, is very similar. In run 2, we were using boosted decision trees and handcrafted variables. And in run 3, we ask a transformer to do the job. So this performance is much better than this performance. This is a logarithmic scale. So the background, if you make this cut, is like 3 or 4 orders of magnitude smaller in this case. So we can use the taggers that we've built to tag heavy flavor and adapt them to look for dark matter. And when you do that, then you improve on the sort of classical cut-based scenario by a huge factor in the limits on the mass of the mediator particle for the shortest lifetimes of dark matter. And you also push yourself up in the range of lifetimes that you can successfully exclude. Um, so we trained this tagger using the same tagger that we used to look for bottom jets, but we gave it an admixture of, beyond the standard model models in order to train it to recognize those. The other thing we could do is anomaly detection. So this was looking for semi-visible jets. Um, and so the tagger was initially trained to find semi-visible jets and then and then retrained to detect anomalies in data. And you can see that not only is it pretty good at looking for these SVJ scenarios, but it also has some discrimination against dark matter. Um, I mean, against the emerging jet scenario. So by an anomaly detection strategy, we will do a great job of looking for the signals that we expected to search for, and an okay job at being sensitive to signals that we hadn't put into the model training. So I can't give you an outlook for the dark jet scenarios because the 2 papers that I just mentioned were out very recently, and the authors have not had time to go back and see what this would look like at the high luminosity LHC. But I can say that it's probably going to look better because our tracker acceptance has increased, so we'll have a broader range to search for various topologies, including T-channel. And for reasons that I'll tell you shortly, we also will have better discriminating power against long-lived, or for, in this case, long-lived particles. But in these 2 cases, one, you have to know exactly what you're looking for and train. In this one, you don't know what you're looking for, but then your sensitivity is reduced because you're using the data to search for it. It would be really great if we could do another version where we plug in the standard model in order to define what normal is, and then we look for outliers in that. And that way we're not making assumptions about what's in the data that we're using to train. But for this, we have to do a much better job of modeling jets. So we've had 3 lessons, and now our homework is going to be to collaborate between theory and experiment in order to improve our understanding and our use of calculations and parton shower models to the point where we can trust our simulation to predict more observables that we would be using in these AI methods. It would also just be nice to have some clean observables that are good at discriminating between the models that we want to search for, but that are not very sensitive to the differences between different approaches to standard model parton showers or between standard model parton showers and what we observe for ordinary data. For this to happen, we'll need a lot of measurements that we could use to tune these models. And both Atlas and CMS are very much involved in creating these measurements, as well as enriched data samples where we know what kinds of particles are in them for training. And I mentioned open data because open data allows a lot of this theory experiment cycle to happen more quickly when the data is not closed inside of one experiment. So examples of some of the maybe more robust variables that we can use in tagging. One is the Lund plane. So this is basically just a representation of the probability distribution that I showed you in one of my early slides for the emissions of radiation in the formation of a jet. And from this probability distribution, you don't see any parameters except for these. So this should be a flat distribution in the log 1 over z, log 1 over r plane. And it is flat, except for the fact that the strong coupling constant evolves to basically small 1 over z and small 1 over r, or more specifically to their product. So along this line, the Along this line, the coupling is stronger, and so there are more emissions. But this is very well modeled. It's been measured and compared with various versions of generators. So you can see here, downward open triangles are string fragmentation, and the sort of gray X's are dipole fragmentation. So there's all of these different models. Or sorry, this is dipole shower. The other one is string versus cluster. Um, and this is decent for a jet observable agreement between all of these models and between our data. There are places where the agreement is not so great. So when you look at things that are more sensitive to hadronization, such as energy correlators at the very small angular scales, you can see much larger deviations between models and data. So this is a place where these kinds of measurements should work to improve our understanding of parton showers. Okay, so I can conclude by telling you a little bit about the future. I think everybody knows that 2026 is the last year for the low luminosity LHC. It will be turned off, upgraded with better focusing magnets, with crab cavities to increase the luminosity by overlapping the bunches better, and other improvements that will allow the luminosity, instantaneous luminosity, to go back by almost a factor of 8. And that means that Atlas has to be ready for luminosity increases and pileup increases of a similar factor. So from our silicon and gas tracking detector, we are changing to an all silicon detector, the ITK or inner tracker. And this will have billions of channels and allow us to read out and hopefully precisely reconstruct track positions through an extended range and rapidity. So the initial tracker was smaller and only went out to about 2, and our new tracker is going to go out to 4 in Eta. There's also a timing detector also put in for rejecting pileup, but also quite useful for looking at slower heavy particles. And I've already showed you all of these projections for what the impact of these improvements will be on the sort of measurements I discussed, the top mass measurements, the dye Higgs production, and on flavor tagging. Now, if you think that's an exciting future, I would agree. And I think it's exciting because now jets can be part of a precision ecosystem. We're no longer separating out jets as places where we only make approximate measurements or measurements about QCD. I cannot deny that if this was a lesson, AI helped us with a lot of our homework, but we have to follow up and understand these increasingly complicated taggers against the data, not just against simulation. And since anomaly detection is possible and it can test these dark sectors that we haven't even imagined, we have a challenge to be able to train these kinds of algorithms with pure standard model samples, or train our parton showers with pure standard model samples, so that we will have the furthest reach. And the animation disappeared. It was going to surprise you by saying that the legacy of the low luminosity LHC so far is not just the discovery of the Higgs boson, but also the instrumentalization of all of the standard model from the strongly interacting and the weakly interacting part as precision tools for discovery. This is something that we will be able to use at each stage of the energy frontier going forward.